Look at these two cups of tea. One is pale and watery, while the other is dark and robust. This visual difference is a signal that the two liquids will behave differently. The difference is concentration, a mathematical ratio. It represents the amount of solute, the tea extract, dispersed within a fixed volume of solvent, the water. On the left, particles are sparse. On the right, they are crowded. Increasing this ratio does more than change the color. It alters the liquid's physical properties, shifting its taste, its viscosity, and the temperature at which it begins to boil. Concentration is a measurable physical transformation of the liquid, defined by how much matter is packed into the mixture. There is a physical limit to this process. A solvent cannot absorb an infinite amount of solute. Eventually, the added substance simply piles up at the bottom of the container. At this point, the liquid is full. This is a saturated solution. The solvent molecules are entirely occupied holding existing solute particles, so any newly added solids have nowhere to go and settle at the bottom. But is it possible to bypass this equilibrium? Can we force a liquid to hold more than its natural limit? This saturation point is a boundary that can be shifted using three specific variables: temperature, pressure, and chemical compatibility. The first variable is temperature. Baking soda dissolves slowly in cold water, but disappears almost immediately when the water is hot. Heat adds kinetic energy to water molecules. Moving faster, they strike solid structures, breaking apart particles to increase solubility. But heat oppositely affects gases. The energy causes dissolved gas particles to vibrate, break free from the liquid's grip, and escape. This explains why fish struggle in warm ponds. As the water temperature rises, it loses the dissolved oxygen that aquatic life needs to breathe. Temperature works in two directions. While heating the solvent allows it to dissolve more solid matter, it simultaneously purges the system of dissolved gases. The second variable is pressure. Squeezing a liquid or a solid does very little to change the mixture because their particles are already packed tightly together. Gases are different. They are highly compressible. According to Henry's law, when external pressure increases, gas molecules are forced into the liquid and trapped there. Inside a sealed soda, high pressure keeps carbon dioxide dissolved. When the cap is removed, the pressure drops instantly, leading to rapid effervescence. In this system, pressure acts as a physical cage that keeps gases in a dissolved state. The final variable isn't about force, but compatibility. Some substances simply reject each other at a molecular level. Water molecules are polar, carrying slight electrical charges. Like magnets, they pull apart other charged substances, like salt. Oil molecules are nonpolar, with no charge. Polar water molecules ignore them, bonding to each other instead, creating a barrier that forces oil to separate. This is the principle of like dissolves like. Polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar ones. Without this chemical compatibility, no amount of heat or pressure can force the substances to form a true solution. These rules determine how we manage road safety in freezing climates. When we spread salt on icy roads, we are using a process called freezing point depression. By increasing the concentration of the solute, the water molecules are physically blocked from forming a rigid ice lattice. This keeps the water liquid even when the temperature drops below freezing. This same science is at work in a simple cup of tea. Achieving the right flavor is a balance of these microscopic forces. The concentration is the result of heat extracting compounds from the leaves, and the water's polarity selecting which flavors to dissolve. Solutions are dynamic systems. By adjusting these variables, we can precisely dictate how substances interact and behave.